Let's learn about push down automata. Push down automata is a 7-tuple machine. The 7 tuples can be represented as Q, sigma, del, tau, Q naught, Z naught, and F. Here Q stands for a finite set of states. Sigma stands for finite input alphabets. Del is a transition. Tau is the stack symbol. Q naught is the starting state. Z naught is the final state. Sorry, F is the final state. Z naught is the initial stack symbol. PDA can be implemented using a stack. The stack operations are push and pop. The push operation is similar to inserting an element. Pop operation is similar to deleting an element. This is an example stack. Elements can be pushed, and here is the top of the stack, and based upon the operation performed on the stack, elements can either be pushed into the stack or it can be popped out from the stack. Let's take a sample language. L is equal to a power n b power n where n greater than or equal to 1, which gets accepted by the PDA. Let's now design a PDA for the language L is equal to a power n b power n where n is greater than or equal to 1. Let the sample string be a b b. It is a valid string. Here n is equal to 2. The first step in designing a PDA is problem description. Here we need to describe how we are going to design the PDA. For this PDA, we use a technique. Whenever we see the input string is A, we need to push the element into the stack. Whenever the input symbol is V, we need to pop. Therefore, the stack gets empty. The second step is to draw a transition diagram. Q naught is the starting state. Next state is Q1. Initially, we need to push the symbol A, and the bottom of the stack will be Z naught. Therefore, now the top of the stack becomes A is not. Then here comes the next state Q2. Then we need to push the A into the stack. This self transition states how many number of times A occurs, it need to be pushed into the stack. If B occurs, we need to pop. Here too we need to include the self transition, so that if there comes more than one B, it will get popped. Next is the final state, we denoted by QF. The last stack symbol will be blank, so we include Z0 and we finish the termination. Here let's see the execution. We took the sample string AAB. First, according to this, A gets pushed, and then pointer comes here and A gets pushed. As B occurs, top of the stack is here, so for the first instance of B, the A gets popped, and then the pointer comes here, and for the next instance of B, the bottom A gets popped, so the bottom will be Z0. Next step of PDA construction will be transition table. The first column is transition, and here is the operation performed. First, for the state Q0, the first transition will be Q0, comma A, comma Z0. For the input symbol A, and the top of the stack is A0, then the top of the stack becomes A Z0, and it moves to the next state Q1. So the operation performed here is push operation. We push the element A, so we denote as push A. Then we need to write the transition for Q1. The first transition for Q1 is del of Q1 comma A, because the top of the stack is A and the input we are going to push is also A. Now A gets pushed, the top of the stack is A, but it remains in the same state Q1. Operation performed is push A. We also have another transition for Q1, that is Q1 comma A comma B, Q1 comma B comma A gives Q2 comma epsilon, which means that the input element is B and the current state is Q1, the top of the stack is A. So whenever we found B, we need to perform the pop operation so that A gets popped. Here the pop operation is performed, so we denote pop A. Then the next state is Q2. Transition here is Q2 comma B comma A. It goes to the same state Q2 and the pop operation is performed. It is a self loop. And we also have another state for Q2. Q2 comma B comma Z0 gives goes to the final state, and therefore the string gets accepted. Um, the next step will be validity checking. In this step, we will try with two examples. We will check one for the valid string, and we take another as an invalid string, and we will execute with the PDA we have designed, and we will check whether our PDA gets executed in a right way for the valid string, and the PDA should not accept the invalid string. Let's now check. We take the valid string as W is equal to AAB blank space invalid string W is equal to ABB blank space. First transition will be del of Q naught comma AABB comma blank comma Z naught. It will be processed as the pointer will be here. The first A will be pushed into the PDA, and therefore as the A is pushed into the PDA, it goes to the state Q1. It becomes ABB and blank space A is not is the top of the stack. Then the pointer is here. The transition becomes Q1 comma BB blank space comma AA Z naught. A is pushed. Now the first instance of B, so the transition becomes Q2 comma B blank space A Z naught. Because for the first instance of V, the top of the stack gets pushed, gets popped, so that for the first instance of B, the first A is popped. Next comes the next instance of B, so the another A also gets popped from the stack. So the state will be Q2 comma blank comma Z naught, which means accepted. For the invalid string, first instance of A is pushed into the stack. Then by seeing the first B, the top of the stack gets popped, therefore now the top of the stack remains Z naught, but there is no A to perform the pop operation, but the input symbol remains B, but we don't have top of the stack A, so it is an invalid string, therefore no transition to proceed. This string is an invalid string which cannot be processed by the PDA we have designed. From this we have justified that the PDA which we have designed is a valid for the language L is equal to A power n B power n, where n greater than or equal to 1.